have to speak up, I guess. Okay.
Okay, so let's welcome Dennis Plat from Wigner Research Center for Physics. We'll talk about correlation functions and Negristore orbifolds from integrability.
Yeah, thanks a lot. Indeed, yeah, correlation functions and N=2 orbifolds from integrability. This is based on work together with Torben Skripek. And also, I mean, I will tell a bit about ongoing work in this regard. But yeah, before we look into the orbifolds, oh, it doesn't do anything. David, do I? Oh, no, it does, sorry. Good. Yeah, before we go into the orbifolds, let's take a look at ADS-CFT again. I mean, Charlotte already said a few things. I will probably say it again, but differently. As you probably all know, the ADS-CFT correspondence connects string theories on ADS space to conformal field theories. The most famous example is, of course, ADS5 crosses 5. So strings on ADS5 crosses 5, which is dual to N=4 super symmetric Young-Mills theory in 4 dimensions. And then in particular, this theory has 6 scalars that we also already heard about, and these will be the interesting fields for me today. A bunch of fermions, and then of course the gauge boson. The coupling constant is of course the Young-Mills coupling constant, and we have some gauge group SUN. And as Charlotte was also mentioning, in the integrability application, we're usually interested in the planar limit. So we take this combination of the coupling constant and the rank of the gauge group, which is the TOF coupling lambda, and then by making the coupling constant very small and the rank of the gauge group very large, while keeping lambda finite, we get this so-called planar limit. So don't get confused. So I called it lambda here, but now I will use G, which is just a rescaling. So for now, my coupling will be G. And of course, this correspondence also states that every observable on the ADS side has a dual observable in the CFT side. And the first thing that people looked at, of course, is the spectrum, so the energy of string states, then related to a anomalous dimension of gauge invariant operators. Okay, so let's quickly review the spectral problem. Of course, we are in the gauge theory, we are interested in calculating the anomalous dimension. So you have the classical scaling dimension and then some corrections depending on the coupling. And as I said, this corresponds to the energy of string states on the string side. So, and now the spectral problem can be mapped to an integrable spin chain. This was the seminal work by Minahan and Zarembo. So let's build a spin chain and start with an SU2 sector that will also appear later again and again in my orbifold examples. So we choose any of these fields, these complex scalars, or the scalar fields that I showed you before, Z, and identify it with spin down. And then we can choose another field, let's say X, and identify it with spin up. And from these fields in the gauge theory, we can of course build a gauge invariant single trace operator. So we take L of these fields and put them on their trace. And then in the spin chain picture, well, you have a chain with L spin down fields. Now we can also add excitations. So for instance, let's put 2. So we insert X's here at some places into this single trace object. And of course, in the spin chain picture, you just flip 2 of your spins and have an excited state. And then the statement is that the planar one-loop dilatation operator from the gauge theory corresponds to a spin chain Hamiltonian. And in particular, here is 1 minus the permutation operator. So with this, we can, of course, use all of our integrability technology and the beta ansatz. So let's take my favorite, the coordinate beta ansatz, where we write down the plane wave function with the S matrix here that is the phase when 2 particles overtake each other and scatter. And then acting with the Hamiltonian, you can work out the energy and the S matrix, everything in terms of these rapidities U that we also already heard about, characterize the system. And in particular, the important thing is that you get this nice set of beta equations where the S matrix, so all these scattering processes factorize into just 2 particle scatterings. And then like the nice way to read this is bringing one of these excitation ones around the chain by this shift factor, so L sides. You just pick up a bunch of scattering phases whenever you overtake another excitation. But of course, it's the same state, so it's one on the right-hand side. And of course, there's also this momentum constraint for this picture. Okay. So this is the spectral problem of N=4 and from integrability. And then about 11 years ago, 2015, also 3-point functions became accessible by integrability. And this was done by Vaso, Komatsu, and Vieira, who introduced this hexagon form factor prescription. So the idea is you take a 3-point function, and we'll look at it in this worldsheet picture, for instance, where it looks like this pair of pants. And now you cut it along these seams here, so these red lines, and then you take it apart, and you get these 2 hexagonal patches. I hope that was more or less clear. But of course, these operators carry excitations, and now the excitations can up either on the front hexagon or the back hexagon. And you have to sum over all these different partitions that you can get with a weight factor that I call omega here and rho here. So I will use rho from now on because omega will appear for the orbifold in another instance. So these hexagon form factors can then be evaluated by just the form factor. You have to take into account this weight factor and to sum over all these partitions. And this weight factor or splitting factor tells you basically what is happening to the excitations. So if you, for instance, starts with, let's say we have 2 excitations, these two blue dots here, and they start on the first hexagon, and then you want to move one of them to the other hexagon, well, you have to move them by a couple of sides over the spin chain, since you cut the spin chain into 2 things. So you move them by L sides. And also, if this excitation set before this excitation first, it has to overtake it, so you also pick up an S matrix. So in this way, the splitting factor keeps track of how the particles move and where they are. And then this, I mean, if you evaluate this hexagon with just this part, you will get the asymptotic results, but you disregard of finite size effections, because of course also on this worldsheet there are virtual particles traveling around the worldsheet and so on. And by cutting it, you kind of lose this information. So you can reinstate it by gluing these 2 patches back together. And how do you do this? Well, you glue by inserting a full set of states on these dashed lines here. So on both hexagons in this way. So you have to sum over all the different flavors of the particles, over any number of particles that you can insert, and then of course also over their momenta. So in practice, it's hard to evaluate, but in principle, this also allows us to calculate 3-point functions. So far so good. Spectral problem, we talked about 3-point function, we talked about for n equals 4. And now the question is, do these methods also work if we go a little bit away from maximal supersymmetry? And of course, like a natural candidate to look at here is our orbifold theories, which still are integrable, but have less supersymmetry. So let's go to the orbifolds. Well, okay, yes. Well, the idea for the orbifold is you start with n equals 4 as the parent theory, and then you identify different configurations that are related by a discrete ZM symmetry. Hopefully it will become a little bit clearer in a moment. So what does it mean? Well, on the string background, basically you replace the S5 by S5 over ZM. And for the gauge theory, you will get a quiver gauge theory. So this is usually the quiver diagrams, necklace diagrams that people draw for this. So in each of these, well, if you stay in the picture of a necklace, pearls on this necklace is a gauge multiplet, which contains the fields, for instance, Z and A and some of the fermions, so the gauge field and the scalar field Z. And these fields here transform under the adjoint representation. So they stay within the same pearl. And then on the beat, I guess. And then we have the hypermultiplets, the fields X and Y are in here and some other fermions that transform under the bifundamental representation. So these are the links between these different beats here. So in particular, like X brings you one further and Y brings you one back. And then invariant operators always have to like take a full circle in this quiver diagram. Okay, so what the orbifold does basically is it introduces phases on some of the fields. So here's this omega and omega to the -1 for X and for Y, while Z is invariant. So you can also think about this as X and Y being charged under the orbifold, while Z is uncharged in that sense. And now I introduce these these gamma matrices here, because of course we want to think about the gauge theory. So all these fields should have gauge indices. So let's write this gamma as a diagonal matrix where the entries on the diagonal are exactly these m roots of unity, and then powers from 0 to m minus 1. And if you then employ this orbifold condition up here, you will find that the only elements of your big matrices that survive are these block matrices. So in particular, maybe let's look at Z first. You have this diagonal matrix where you have n cross n matrices on the diagonal, and then you have m of them. So it's like a big nm cross nm matrix in total. And then for the x's, you are on the upper diagonal, and for the y's on the lower diagonal. And this basically makes exactly sure that these fields transform under this way when acting with gamma. Okay, so we looked at the fields. So what do the single trace operators like that I introduced earlier? So we can build this in the same way. So we have some fields xz, for instance, and we introduce this gamma k here in the beginning. And also let's look at the Z2 orbifold since it's simpler. So, and then of course you can just multiply out these matrices that I gave you, and what you'll find is that you have this sequence of numbers, I mean of the gauge groups that it transforms under, and in particular it's closed. So otherwise it would be projected out by the orbifold. So we start with the 1 and we end with the 1, and here we start with the 2 and we end with the 2, but we also pick up this factor omega to the k here because it's basically like a different part of the set. Okay, so now we can also act with the one loop dilatation operator as we did before to find the spectrum. And for the untwisted case, k equals 0, everything looks like an n equals 4. We get the energy E is equal to 4. And then for the twisted case, k equals 1. Well, the gamma is really here, and we have this. We have a minus 1 since the root of unity is minus 1. Then you find this is the eigenstate, and the energy is shifted. And in particular, I mean, what does this gamma do here? Well, it's something like a twisted boundary condition, because if I take a field Z here and move it once around the chain, I mean, it's a trace, it's cyclic, then I may have or not to pick up an omega depending on these relations when I move over the gamma. So this is the kind of important message here, that just by introducing this roots of unity, I already changed the spectrum and the eigenfunctions. Okay, let's generalize notation a little bit and just speak about excitations and vacuums, because I can also use different combination of these fields to build operators and spin chains. So we have vacuums and excitations that we identify with down and up again. We have these Ks that tell us in which twisted sector we are, and it's basically just this twisted boundary condition that if I take the last side and put it to the front, I shift the chain by one side, I pick up an omega factor depending on this. Then of course the coordinate beta ansatz looks exactly like before. I just have to implement this twisted boundary condition, and then I can work out the beta equations that also look like the beta equations you saw in N+4. The only difference is on the right side here, I have these omega factors showing up with, of course, the twist sector k, but also these additional, there's p and p minus q that basically tell us in which sector we are sitting. So for instance, if you look at the thing that we had before, where we have the vacuum z, and then on top we put x's, then p would be 0 and q would be 1. But I could also, for instance, choose something where I have a vacuum x, which is already charged, and p would be 1, and then some excitations y bar, where q would also be 1. So in this sense, you can have a real big set of different beta equations and sectors that you can consider. Okay, so that was the spectrum. Now the big question, does it also work like this for orbifold theories, for 3-point functions? Sorry, thanks. And the question is yes. Well, you have, of course, to make sure that the total amount of twist that you introduce in this figure is invariant under the orbifold condition. So all the operators together have to be 0 mod m. Then, of course, you have some twist lines running here now over the hexagons after you cut the 3-point function. But apart from that, the evaluation is more or less the same that we saw before. There is one conceptual problem in the beginning, and this is in the construction of these 3-point functions. You use some super translation generator T, and since the orbifold breaks asymmetry, also the super translation generator is broken. And also in the beginning, this created some conceptual difficulties for us, but the answer seems to be that you only project on physical states at the very end, and then you can really calculate physical quantities. Yeah, and then finally, where does the twist enter? Well, of course, it enters once through the rapidities, because the rapidities that I put into the evaluation of these formulas are the rapidities that I get from the twisted beta equations. So this is how the spectrum changes. They know about the twist. And then the other thing is that we have the splitting factor rho here. And of course, if I move a particle over a twist line, then according to this orbifold commutation relations, I have to pick up an omega factor, an additional omega factor. Hello? Okay. So you can also look at this asymptotic. I mean, at first we looked only at tree-level things. Then you can ask, does it also work if you look at asymptotic three-point function, and for instance at one loop? Yes, it works. The only thing you have to make sure of is that you can disregard finite size corrections. So the three-point function, for instance, be not an extremal. And then, of course, you just use the asymptotic expressions for the evaluation. And indeed, we found perfect agreement. I mean, you just have to calculate. So we calculated two twisted operators and one untwisted operator. So the first one is untwisted, and these two would be twisted, carrying excitations as well. And of course, all of this has to be checked against field theory results. On the one hand, you could do honest field theory and really draw all the graphs with all the calculation. We decided to use the Hamiltonian insertion method, which is much nicer. The idea here is you just construct the two-loop eigenstates from, for instance, the dilatation operator, and then you insert Hamiltonians at the splitting points of the operator. So for instance here, but of course we would also have to insert one between here, and then for the other operator on the bottom. So in total 4 terms that you have to sum over, but then you get the asymptotic results also from field theory. And as I was already saying, in all these cases, we found perfect agreement with the hexagon. So we also looked at the different sectors. I mean, if you remember this table where I can pick different combinations of SU2 sectors. Okay, then one last question: how should the twist line be distributed over the hexagon? I mean, I put this now here, but of course I could also like form this whole thing and put it on these edges, for instance. Asymptotically, so far, it seems that the equivalence between all these 3 ways are governed by the beta equations, basically. I mean, in particular, these splitting factors. So these keep track over the excitations moving over the edges of the hexagon and then pick up the appropriate factors. So that seems not a problem. But of course, what happens if you consider finite size corrections? Because I told you earlier, if you glue, you put them on these dashed lines here. And then these particles seem very much sensitive to these twist lines. But of course, this has to also be consistent with localization results in the literature, where also there was already some matching from hexagons. They're only for protected 3-point functions that are extremal, because these are what is in the literature for the localization results. But still, it would be interesting to understand how this changes in the presence of physical excitations and finite size corrections. Okay, so let me briefly conclude and give a small outlook. So I hope I convinced you that the hexagon formalism for non-BPS operators and n = 2 orbifold theories works pretty much as an n = 4. The only, very much like for the spectral problem, the only thing you have to keep track of is that the rapidities u change since you use the twisted beta equation to solve for them. And then also the splitting factors might pick up some additional twist factors depending on where you distribute them over your figure and where the excitations move then. I briefly told you that the super translation mixes different multiplets and is one of the obstacles in this construction. But in the end, you just project on physical states and then everything's fine. I also explained that asymptotically these twist lines can be moved over the figure. And we also checked this against gauge theory and overlap calculations at one loop order at least for various structure constants computed in the Z2 and Z3 orbifold. And from here, of course, you can also generalize to higher Zm orbifolds. And then finally, where will this all lead now? Well, I mean, a promising approach, like orthogonal to the hexagon form factor, I would say, is the separation of variable formalism. I mean, Paul will talk about this later, which also seems very efficient in getting the same structure constants that we calculated. So I'm interested in hearing about this. And then, of course, what we are looking at the moment is these finite size effects, where, of course, we already know that matching of localization results is possible due to these guys. And for us, the question now is, can we also come up with gluing rules for non-extremal correlators? But of course, for this, we also need, once again, field theory data. And this is, of course, a little more involved. All right. Thank you very much.
You questions?
So about the matching of extremal correlators, I suppose that there will be also some mixing with double trace, right? Is it something that you have looked at, or maybe is not relevant here?
I mean, well, the extremal correlators was done by Ferrando Komatsu, Lifundis, and Servan. But here also, it's only BPS operators. So I think there is no mixing. I mean, you have non-trivial effects, but these are basically, I guess, due to the normalization of the two-point function.
So I'm not sure in orbifold theories, but you could conceivably have mixing even in the BPS sector.
Even for, okay.
Yes.
All right. But then, yeah, the usual problem. Listen.
Question: Are there any interesting scaling limits of this twist when you take it to infinity, 0, whatever?
I've never thought about it. I mean, well, of course, you can like go to long quivers and so on, where you put that M very, very large, and then basically this omega becomes continuous. I know that people are also looking into this. We at the moment are happy with this low order.
Okay. There are no further questions. Dennis again.
Thanks a lot.
And as we